I'm going to be talking about online change point detection using Spark streaming. So my name is Michal. Monselise. A bit about me, I'm a senior data scientist at DSIQ, where I work on the research team and I create prototypes to optimize marketing campaigns. I'm also an instructor at University of Washington School of Continuing Studies, where I currently teach a class on data engineering. Okay, so I thought I'd start to discuss the importance of change point detection by talking about a few examples. So I'm going to talk about genomics, marketing, and finance. And so in genomics, we can examine the change points in the ACGH profile, which is the comparative genomic hybridization profile of DNA, and we can use that to identify involvement of genes in cancer or other diseases. So we use the change points to detect that. And then in marketing, so this is kind of a graph of data, a time series data and change points in the data. And in marketing, we could identify things like churn or customer engagement changes. So this is very useful for areas like online retail. So we can adapt much faster to customer behavior. And in finance, so this is Microsoft's stock between 2015 and 2016. So there was a huge change point around September, and so theoretically, if you could pick up on that change point, you could make a lot of money. So I know that stocks don't quite have a theoretical distribution, but you could see that there was a big change in the stock price. Okay, so in the past, change point methodologies took a batch of historical data, and then they would look for the change points in that historical data. And so this is useful for some cases, but when we look at streaming, we want to be able to detect whether the data, there's a change point as the data comes in. Spark streaming is actually perfectly suited for this use case. So that's the thing I used in my project. All right, so in trying to figure out what is the best way to detect change points in real time as data comes in a stream, I looked at a lot of research, and the two main studies that I found were the most suited for this use case were a non-parametric algorithm and a Bayesian statistics algorithm. And so in the non-parametric method, we have two windows, and each one contains n observations, and window one contains the most recent n, and the second window contains one before that. And so we find the distance function that we define, and it's up to us, the user, to define the distance function based on what suits us. And so that's where the non-parametric part can come in. And so if this distance is greater than an alpha, then we say that there was a change point in the data. And so in the Bayesian area, if we look at Bayes' theorem, for those of you who are not familiar with Bayesian statistics, what Bayes' theorem is a theorem for computing conditional probability. And so in the area of Bayesian statistics, we basically say that we have P of A, right, the probability of A. That's our initial assumption about the data, about the distribution of the data. And so we start off with our prior distribution, the P of A, and then as data comes in, that data is our observed data or our likelihood. And so when we take the product of those two, just simply the product, so our posterior, our actual distribution, what we assume to be the distribution of the data, is proportionate to a product of those two, the prior assumption and the likelihood, so the actual data, the observed data. Okay, so using a Bayesian algorithm means exactly that as new data comes in, like we start with a prior assumption, As new data comes in, we keep updating our assumptions, updating our distribution. So this suits our needs perfectly for detecting online change points. Yes?
So can we see the change point by updating just one data point, or what is like the set of point that what we can see the difference in the both distribution compared with the previous distribution? So normally, like, how do we know how many points we update in order to see the difference? Because one point probably not.
Yeah, there is a burn-in. Usually in statistics, in Bayesian statistics, we like to have like a burn-in period. But the first point, so I'll get to it here. So the first point always, so we're modeling the number of observations till a change point. So when you have a change point, you will have had 0 observations till a change point, because right now we're at a change point. So the first observation is always going to be a 0, right? Right now we don't have anything prior, so it's going to be a change point. And then as new data comes in, we create our Bayesian distribution as more and more data comes in, and then we can look for another change point, and then again the number of data points till a change point is 0, and so on. So we have this p gap, right, the distribution between change points. So every time we have a change point, we basically evaluate based on that p gap, the distribution till the change point. So we're using the hazard function over here, and as I mentioned in answering the question, we have RT, which is the number of observations till a change point, and we start off with 0, and as we progress, we increment it by 1. Every time we don't see a change point until we see a change point, and then it's 0 again. So modeling this instead of looking at the data gives us better results. Okay, so there are limitations, and that's where our window function comes back. And so in theory, it's nice. We can, as data comes in, we can keep updating our distribution. But in streaming, theoretically, we could have data that goes till infinity. So if we're doing something like matrix operations, it can become very cumbersome. And so we need to come up with a solution so this doesn't get out of hand. And so a good example is global warming. So if we want to determine if there's an increase in temperature today, we don't look at measurements from the dawn of time. We'll look at the last 100 years or even 200, but we don't care for thousands of years ago. So it's a reasonable assumption to make that you can pick a large window of observations in computing your posterior distribution. And then, because we're using Spark, so I wanted to just introduce accumulators. So accumulators are a variable in Spark that can retain information from prior microbatches. So the way Spark works, Spark streaming works, is that you get microbatches and you process them, but there's no memory between them. So every time you'll just process the batch as it comes in. But accumulators can store information about previous batches. And so in this case, so you can create by default a numeric one. I think the simplest one is just to take a sum as data comes in to accumulate, right? And then, but here I created an accumulator queue, and the accumulator queue is of size max queue size. And so I made it pretty large, but once you hit that limit, you're just keeping the last max queue size observations. So here I have my definition of the queue, the accumulator queue. So we define the accumulator with a dequeue, right, in Python, and then it's of max queue size. And then you define it as a global, so the whole program can see it. So a case study I looked at is weather. So in my company, we look a lot at weather and how it changes consumer behavior and sales. And so one way to look at weather is to look at right, the number of standard deviations from the mean. If people perceive something to be hot or cold, is it 2 standard deviations from like in Florida, 2 standard deviations from the mean is very different from Nebraska's 2 standard deviations from the mean, or Alaska's 2 standard deviations from the mean. But we've noticed that sometimes consumer behavior will change more if there's a big shift, a big drop in temperature, rather than if we have something that's bigger in variation. So I looked at the temperature for zip code 98006, which is Bellevue. And I looked at temperature from September 2016 to February 2017. And identifying the change points in this data will help us identify abrupt temperature shifts. So as I said, our hypothesis is that sudden changes in weather influence consumer behavior more than absolute temperatures. And we also think that these changes influence behavior more than relative temperature. Okay, so I'm going to go into a demo. So I've created a PySpark streaming script that basically takes our, this is kind of black. Yeah, sure. Oh, yeah, sure. Is it good enough? Okay. So on one hand, I have a Kafka queue, and in this case, just for the demo, I write to the topic the weather between September and February, and so that's our peak winter season, and we wanted to look at products that are related to cold weather and whether they're influenced by shifts in temperature. And then I also have a Spark, as I said, a Spark streaming script, and it has an accumulator, and I keep writing to the accumulator and creating a n plus 1 by n plus 1 matrix, and that I compute the contour. So I'll show you that in a second. Okay, so if I run this, this takes 10 seconds. So I'm going to be writing to the queue. I put in a 1-second sleep in between so that it comes in as a micro batch of 1 line. So every time Spark runs, we get 1 temperature observation, and then I create a like I said, a matrix, and I compute the probabilities for the contour plot. So over here, as I mentioned, there's a burn-in period. So in the beginning, it just says, so this would be the output of that Spark job. So in the beginning, we have, it just says, there's like I said, there's a burn-in period, and we say there's no change points. But after a while, it starts picking up on the change points, and so each white line slope basically says that, this is a time period where weather is stable, and then it drops to 0. Right, there's been a change point in the weather, and it goes up again and drops again, and so the GIF is just playing and repeat. So Spark job creates the numbers to create this contour plot. Yes.
How do you deal with the not a sudden change, but gradual change? For example, in some of the manufacturing scenarios, data doesn't change immediately, but rather, for example, a downward trend of some metric that represents some problem. So how do you deal with that kind of gradual change like that?
So the question was, how do we deal with a slow change? Well, we're not interested in detecting those because we make an assumption that they don't really influence behavior as much. So we're just interested in big spikes. And so we want those spikes to be kind of more relative to the environment. And we don't want to just define, oh, if temperature went down by 10 degrees, then trigger, some cold weather, like a snow advertising campaign. We don't want that. We want to know if temperature just went down abruptly. So we use this algorithm to define what abruptly means. Okay. So additionally, I plotted, yes?
Quick question. Do you worry about like spurious correlations in that abrupt drop in temperature?
Yes, sure.
So do you worry about like spurious correlations in that abrupt drop in temperature? Like especially looking at Bellevue in that season, like the temperature actually drops a lot on the clear days. So it could be, in fact, a correlation with sunny versus not sunny. And so does this, I guess, when you're looking for this, like what is an abrupt drop, do you do any sort of like false data checking first? Or are you just trying to find like 5 degrees is a good drop? Or
So I think what we're doing is first we're identifying the drops, and then we're evaluating the scenarios where that happened. Like you said, if it happened because of something else, then we're going to roll those out. So we're checking other weather variables.
okay,
Like you said. So
okay. And then do you also set minimums on the time frame that this has to occur in?
yeah, only in winter.
I mean, but like over like a 2-day range, a 2-hour range.
Oh, I see. No, we just get a daily temperature. I think we might get every 6 hours, actually.
Okay.
So we just look at what was the change between those two measurements as the data comes in.
Okay. Thank you.
Every second?
Yeah. I'm sorry?
Every second, if you take a big change, then you tag it as the anomaly. Like every second, like the next point coming in is very different from the first point, and you can see that as an anomaly.
So
What's the window for you? Like, what the window for you to consider?
I see. You're saying if there's an anomaly in the data.
Yeah, what I'm saying is, do you establish a window? Let's say it's not just. I mean, sometimes there are data error, right? One particular point may represent a big change from the previous point, but that's just a data error, and then you consider like, okay, at least the anomalous data must be like 5 consecutive points before you consider as an anomaly, or you just
Yeah. So you define your hazard function, and you define what you're comparing to. So that kind of, you can tweak the parameters of, like let's say one anomaly might be, won't influence as much, so it will take like a critical mass, maybe 2, or I guess it depends on the hazard function that you define.
I suggest to keep the question to the end of the talk.
Okay.
In order to finish. Thank you.
Sure. And then, so that was just one zip code, but if you look at the entire United States, you get this interesting period. I plotted high posterior probability, so the high probability of a change point over a 2-month period. And you can see kind of it goes the same as kind of the weather pattern. So I think this chart kind of validates that the methodology, and I've charted it against weather, and you can see the big spikes. And also, I've charted this against sales, and it's interesting to see that some products that are related to winter will sell well a day after the cold front kind of passes through in the United States. I can't really show that because it's customer data, but so this methodology is pretty good at picking up on these trends. Okay. All right, so any other questions? Because I think this talk was kind of, I'm sorry?
Let's keep the question to the end of the talk.
Oh, well, I'm finished. So.
Ah, you're done. Okay, good. Oh.
What's your underlying distribution, and how do you pick the prior?
Oh, so here I use just a constant hazard, and I used a t-distribution. How do I pick? I guess it would depend on, right, you make a prior assumption. So based on the behavior of the data.
So it's constant hazard, so is that like exponential distribution, and then you pick the prior because you use the exponential distribution?
I think it was, you call it a exponential family, right?
Right.
That's what you mean. Yeah, I think
Can you bring back the slide on the YouTube?
Next question.
Where is it? This.
I saw you were using Kafka, and I was wondering.
Where's the question? Yeah.
Oh, yeah.
Mm-hmm.
And I was wondering if we can see the producer code that you use for Kafka, and also if you were using multiple, you were gathering this information from multiple locations, and if at some point you were using akka for it.
No, I mean, this is just for, this is like my code for the demo. It's a prototype, so,
Oh, just one.
you know, what happened like in my company, I wouldn't have the production code for how many sources they would, you know, if they used akka or, you know, those type of things. But they do use Kafka as well. I can show you my code.
Sure.
For the producer.
Just while we're bringing that up, a quick announcement. Lunch is outside in the hallway, so when you've finished enjoying your time here and there's absolutely no rush to leave, you can go out and pick up a boxed lunch and take that. We're going to be showing some interviews from the live stream in Cascade, which is the next auditorium across. So if you'd like to sit down there and watch a more in-depth time with Andy Terrell, who spoke this morning, and also some people from Microsoft who helped organize the conference, feel free to go and sit in there and have your lunch in there to watch the live stream interview. Otherwise, we'll be going back to McKinley for around about 1 o'clock for the next keynote from Jake Vanderplas. Thanks.
Okay. Yeah, so I basically take, just for this demo, because I'm not going to really read data from NOAA in real time, I just take a CSV file where I had my data from NOAA, and I pass it into the stream for the topic 1 second, with 1 second delay. So each, the idea here is that each microbatch should have one observation, because that simulates what happens in real life. We don't have two temperature readings coming in at once. So just the data from Bellevue and just the minimum temperature for that day, for each day in the time period. And then I turned off the logging.
Hi.
Yes.
Is it possible to share the slides with us?
I'm sorry?
Is it possible to share the slides, the presentation slide?
To share the slides.
Yeah.
What do you mean?
To share the slides, the presentation.
I'll go back to the slide.
Could you share this slide?
I mean, they should be on, like I send them to the organizer, so they should be shared probably after the event.
Okay. Well, because I went to your GitHub, I saw the code, but I couldn't find the slide.
Oh yeah, it should probably after the event.
Slides there too, in the GitHub.
On my GitHub? I can put it on my GitHub then. Okay.
Can you comment about the choice of this model compared to a model that actually modeled the time series, like a RIMA model, and then like using the RIMA model to see when you have a large deviation?
What do you mean?
So an alternative to this model, because you want to find. Sorry. Share. Okay, so an alternative to this model, you can actually use a time series model and look for a deviation in that model. So when an unpredictable value is coming next, that will point to a change point, right?
Yeah.
And can you comment about the differences and why one method will be better than another?
I mean, I don't know if I'm familiar with that method, and I don't know if one is better than the other necessarily. I just chose to use this one, tested it, and so I didn't quite test how this would perform with an ARIMA model, but definitely it is an option.
Okay, how did you define the threshold value so that you name some data point as an anomalous?
I'm sorry. So how
did you define
the threshold?
Yeah, the threshold.
Oh yeah. So the threshold will depend on, I think, that's actually something we're researching right now. So we're developing like how to detect the threshold. But for what I looked at, like 0.5 is a safe threshold. Any probability above 0.5. So.
Any more questions? Okay.
So follow up with his question. Do you compare the non-parametric method and this Bayesian method, and which one?
I didn't. The reason I cited that paper is because I got the idea of using Windows from that paper, like a window, not Windows, the operating system. That's why I used that paper. But you could use that paper. We would have to develop, your own distance function.
Any more questions? Okay, thank you so much.
Thank you.
And by this, we close the session for today. Time for lunch.